So let's go ahead and we'll build the full adder in CMOS. We'll start off with the sum section, and the next page we'll do the carry. So this is the truth table here, and you see that I've got the inputs A, B and the C in, so that's the carry in. But in the diagrams here I've just called the carry in C. Okay, so this C here is the C in. So we've got the sum column here, but what we want access to is the inverse of the sum, because that's what we're going to be generating here. And once we've generated the inverse of the sum, in order to get actual sum, we'll put the final value through an inverter. So we've got the inverse sum here in this column. So this is a column we're actually interested in. And what we want to do is follow the route that we've seen in the previous page. So what we could do first of all is we can write out the actual function for the pull up network and also the pull down network. So we've already seen the pull down network in a previous video when we looked at the full adder, but let's talk through it all anyway. So if the output here, it says is a 0, remember the output we're talking about is not this sum here, it's the inverse sum, it's this one here. So if the output is a 0, then we're going to have a pull down network. So that means that if you look here, there's going to be 1, 2, 3, 4 pull down networks. Okay, so there's 4 networks that are going to be in parallel, and that's the 4 networks there, 1, 2, 3 and 4. So those are 4 pull down networks. And it says here that the values of those networks are going to be the Boolean values of our inputs A, B and C. So the Boolean values for these inputs are simply going to be the first one here, which is a 0, is going to be the not A, not B, C. And you can see I've got not A, not B and C. And I've put the values in here in the actual first network, which is not A, not B, C. Now the very next one down is this one, and it's going to be the value of not A, B, not C. That'll be not A, B, not C, which is this one, and I've got them in here, not A, B, not C. And we do the same for the other two. We've got a 0 here, and it's going to give us an A, not B, not C. So that's A, not B, not C, and there's the network there, A, not B, not C. And finally, the last one here, the value of 0, is going to give us A, B and C. And we've got the A, B and C here, and this is the network for A, B and C. So these are our 4 pull down networks. Now if we were go ahead now and we'll look at the pull up networks, and from the description down here it says if the output is a 1, then we have a pull up network in which the inputs are the Boolean complements of the values A, B, and in this case A, B and C. So let's go ahead and we'll generate those just now. So we're interested in this column here, which is the not sum, and we're looking for the output being a value of 1. So that's output being a value of 1. But what we're going to do here, instead of taking the value for A, B and C, we're going to take the complement. So A, B and C are 0, 0, 0. So in effect the complement would be 1, 1, 1. So this output here then would be A, B, C. And you can see here we've generated that here, A, B and C, and we've put that down in this first series cell here. So that's A, B and C. Now the second one down here is a value of 1, and it's going to in this case be the complement of this. So that's going to be in effect A, not B, not C, and we've got the A, not B, not C, and we've got A, not B, not C. And the third one here is going to be the value here of not A, B, not C. So we're going to have our not A, B, not C. The third one down here, no, it's this one here, not A, B, not C, which is this one. And that's going to be this one here, not A, B, not C. And the very last one here is this value 1, which is going to be the not A, not B, C. And that's the not A, not B, C. And we can see we've got it here, not A, not B, C. So this full network here is going to give us the inverse of the sum. So if we were to actually generate the sum, we could take the output here and we could just put it through a CMOS inverter and get the value of the sum. So this is our network here for the sum, our network for a CMOS full adder sum section. But of course we can actually simplify this a little bit, as we've seen in previous videos, but we're going to leave it just as it is for the moment. There's no need for us to simplify it here. So let's go ahead and we'll move on and we'll look at the carry section. So let's look at the CMOS full adder carry section. This is the truth table for the carry here. So we have the carry and we've also got the not carry. Now we could generate the same architecture for the carry as we did for the sum. That is, we could look at all of the values for ones and all the values of zeros, and we can create the inputs and the negation of the inputs as we did in the previous page using this little process here. So in that case we would end up with 8 lots of 3 transistors. So again we would end up with 24 transistors, just like we did with the sum. But we're not going to work through that process here because we can simplify this down to from the 24 down to 10 transistors. So in order to do that, what we're going to do is we'll just look at it in terms of the pull-up network and the pull-down network. So in terms of the pull-down network, as we say, we've worked through this before. If we were to take the not carry, so this is the not carry here, and we were to look at the values for the output being 0, so this is in effect the same sort of process we would do whenever we were looking at the NMOS pull-down. We would have a 0 here. In order to get the 0, we would have there would be a not A, B, C, and that is that not A, B, C here, and then we could go down to the next 0 here, and it's going to give us our A, not B, C. That's A, not B, C. We can go down to this 0 here and give us A, B, not C, A, B, not C, and this one here is going to give us the A, B, C, and that's the A, B, C here. And we worked through a little bit of Boolean algebra, so we've seen this in a previous video. We'll take out the common factor of the BC from this one here and also this one here, and it will leave us the A, not A, and we add these together, we get a value of 1. And we could do the same for the AC and the AB, and we're left with these 3 here. So that means that the pull down network can be done as B in series with C, and A in series with C, and A in series with B, and each of them are going to be in parallel. So this would be the pull down network. Now, as we've seen whenever we did the NOR and the NAND gate, in order to go from this pull down network, which is the NMOS pull down network, to the CMOS pull up network, what we can do is we can take the series combinations and make them parallel, and we can take the parallel combinations and make them series combinations. And that's just what we've done here. So if you look at this one instance here, we could look at this and simply say, well, we've got A is going to be in parallel with the value of B, so we make AB in series, so we've put AB in series here. And the same thing here, we could say that our other 2 values, AC, so we could say A is in parallel with C, so what we'll do is we'll make A in series with C, and we do the same with the B and the C. B is in parallel with C, so we make B in series with C. So we're ended up with this structure here, and it's got 12 transistors in it. Now, as we've seen in a previous video, we could actually get rid of this transistor here, and we can connect this point here to this point, because the B is going to go through this C here. Now we could do the same, we could get rid of this transistor and we could connect this point over to this point. So that's going to leave us, instead of the 24 transistors, if we had worked through the full process here, with only the 10 transistors that you see here. Now, one other way to look at this network here is to analyse the truth table overall. So in this case here, we could say, how do we generate the pull down network? Well, the pull down network's generated by the low at this not carry. And we say, when do we get a low at the not carry? Well, in this case here, if you look at it, you can see we're going to get a low at this not carry if we've got at least two values of 1. Okay, so there's 2 1s here, and we're going to get a low when there's 2 1s here, and we'll get a low when there's the 2 1s, and a low when there's 2 1s. Equally, we can say what's going to happen, how do we get the high values? So we're going to get the high values here if we've got at least 2 low values at the input. So in this case it's a high, and we've got at least 2 low values here. That's high, we'll get at least 2 low values, and the same for this one and the same for this one. So that means that we're going to have, for the pull down network, at least 2 for the pull down network, we're going to have at least 2 high values, and for the pull up network, we're going to have at least 2 low values. So that's another way of looking at this and to generate this little section here. But I think the best way of looking at this is actually via the truth table here and working through and generating the function and simplifying the function, and then changing it from the series combination into a parallel combination, or alternatively the parallel combination into a series combination, and it's going to give you a minimal help to give you a minimal result. So that's all there is for this video. I'll get you on the next video. Goodbye.